So I'm hoping there's not too much of a lag with this program. Something's happening today with my computer. Not the greatest. I apologize. We're going to continue here. Now that we know water a little bit, we talked a little bit how it changes state. That allows us to build this model called the hydrologic or the water cycle. Probably a familiar concept to you. And what this just states, and what this map shows you basically, to sum it up, excuse me, is that on Earth, water moves through all its various states, solid, liquid, gas, moves through its various environments, the atmosphere, the lithosphere, and the hydrosphere, and it moves through an irregular process that is driven by the sun. The sun is the source of energy that changes the matter that is water. So sun provides the energy that causes evaporation, where water changes from liquid to a gas. As we'll learn about the sun, it also drives the winds that move clouds to where they form inland and condensate, where the water vapor and the water in the clouds turns into rain or snow, which falls back down to earth, which then comes back down to rivers and lakes where it is evaporated and goes through this cycle. Almost all the water in the atmosphere, by the way, comes from our oceans. The great majority of it is. There is a small amount that comes from plants and people. We all give off a little bit of water vapor, actually, when we breathe. Now, one of the things that also drives weather, and we'll learn more about this, especially when we cover hurricanes and thunderstorms, is this concept of latent heat. So remember we talked about water. In order for water to change states, right, you have to either remove or add temperature. And we said before that to change the temperature of water by 1 degree, you have to add 1 calorie of temperature. So 1 calorie of energy. 1 calorie of energy will raise 1 gram of water's temperature by 1 degree. So if you have a gram of water and you go from 0 degrees Celsius to 100 degrees Celsius, so from just melted to just before it boils, that's 100 degrees, right? You would need 100 calories of energy. You see right here. But notice this big jump. To make water go from a liquid state to a vapor state, to make that kind of leap between states of matter, if you're going from a liquid to a vapor, you need to break those bonds, those hydrogen bonds. You need an extra push of energy just to kind of get it over the edge. So instead of 1 degree to go from 100 degrees to 101, you need 540 calories, or an extra boost, like you're stomping on the gas pedal to get going. So to go from 0 to 120, you would go from 0 degrees to 120. That's 120 degrees, so you would need 120 calories plus 540. So 540 plus 120 is 660 calories to go 120 degrees because of that boundary. There's a smaller one here to go from solid to liquid. So to go from a solid state of matter, ice, at 0 to liquid at 1 degree, you need 80 calories. Conversely, if you're going the opposite way, if you want to turn water vapor into liquid, you need to lower the temperature or remove the energy somehow. And you need to remove, to go from a gaseous to a liquid state, you need to remove 540 calories or pull that heat out somehow. And same thing with water. Again, we're not going to cover sublimation deposition too much, but the reason this does happen is if something happens to ice and so much energy is added all at once, basically you have that huge jump here is enough, you can overcome that step. That's a lot of energy to happen, so that's why it's very rare. But that leads to this unique process. So evaporation, to go from liquid to a gas, you need a lot of energy. And so you pull energy from around you in the form of heat, and that heat is pulled away. So evaporation actually pulls in heat, which means that it cools its surroundings. This is why if you've ever had water on your skin in the form of sweat, or just water from a sponge or a cloth, and the water evaporates, you blow on it, you feel cooler, because that evaporation pulls heat from your skin. Evaporation is a cooling process. In fact, condensation is the opposite. Condensation is a warming process, right? And this is the drivers, basically the energy forms that drive a lot of weather patterns. So when water turns into vapor and goes into the air can only hold so much water vapor at one time. Think of it like a sponge. There's only so much. And if you fill a sponge with water, any new water just runs off. If the atmosphere is full, it's said to be saturated. Okay? It can't hold any more water vapor. And then any more water that is trying to add to that will not turn into vapor. It'll just stay liquid. That's when you have clouds. So if you have water wants to turn into water vapor or into steam or into water vapor, it evaporates. But if at a certain point the air can't hold anymore, then the water just stays liquid. And what clouds are not gas. They're not actually steam. Clouds are just billions of tiny little water drops that are so small they can float. And the air keeps them as water because it is condensate, it's saturated. But that level of saturation has to deal with humidity. So we're going to talk about humidity. There's a lot of different things that cover this. The big thing I want you to get from this, ignore evapotranspiration, is that we can measure humidity. We know, we hear the news, it's 75% humid out, right? High or low humidity. How do we do that? The sling psychrometer is kind of fun. It's this tool, you hold it with a handle right here. And I pointed, you can't see it. This arm swings around. So you spin it like a top. And as it spins, it has two thermometers. One thermometer has a dry end, one has an end that's covered in water. And so it measures the wet air temperature and the dry air temperature. If there's a difference, you have a little chart. 2 degrees means it's, say, 15% humid. But if you've ever had a bad hair day, there is science behind this. Hair responds to humidity. When it's more humid or less humid, it'll actually shrink or grow, right? So that is actually not a myth. Your hair will react to the humidity, some more than others, but it can usually be done on a measurable basis. And so a hydrometer is a hair hydrometer, has a series of hairs, sometimes horse, sometimes human right here, between two bars that can move. And the amount of humidity in the air will cause this hair to either shrink or contract, which pulls upon this lever, and it marks on a piece of paper. So all that being said, we can measure humidity. This map shows basic general patterns. I believe it's a 5-year average for the year 2000-2005. The darker the red, the higher the average humidity. And we notice a couple things. The most humid air tends to be where? Pretty simple, right? Right around the equator. As you go north or south, what do we notice? It gets drier, less humidity. We also know from previous lectures that as we go north or south, it gets colder. So there's a relationship here, right? The warmer someplace is, the more humid it is. And how do I know that to be true? Look over here. Remember we said Siberia, or the Tibetan Plateau last chapter is a very cold area? You can see right here that it's actually usually much drier north or south of it. The other thing you'll notice is that it's usually less humid over land. The highest humidities tend to be, for the most part, over open water. There are two exceptions here. Here's the Amazon rainforest. Here's the African rainforest. And remember we mentioned before that plants give off humidity when they breathe. So here you see evidence of that. So this kind of all ties together to see these patterns that we see. All right. Now, many of you have probably heard that phrase, how hot is it? It's 100 degrees, but it feels like 105, right? The heat index. So remember, temperature is energy. We don't feel temperature, but we perceive it as heat, right? If it feels that hot, that's how we perceive it. Now, if you add in water vapor, right, that changes things. Because if the atmosphere has a lot of water in it, so it's very close to saturation, the air is holding 95% of the water vapor it can. That means that it's not going to be able to hold much more, so it's going to slow down evaporation, like us sweating. Our sweat will evaporate slower because the air is already full. And if our sweat evaporates slower, we cool off less efficiently. So in other words, if it's a very humid air mass that we are in, we can't cool down as effectively. our bodies perceive the temperature as being even higher. So that's why quite often in the summer in Chicago, you will see that the temperature outside is 85 degrees, but with the humidity, it feels like it's 95. And this is a very common event in heat waves. Heat waves are usually almost always involving high heat index temperatures as well. Heat waves kill more people every year in the United States than almost anything else. And a lot of people don't think about it. How do you die from a heat wave? Well, I'm going to pause the video right here. I strongly suggest this is a live link, but I'm also going to include the video in the video lecture chapter so you can watch it on your own. This is a live newscast from 1995. So watch that and then come back for the next part and we'll talk about it.